Imagine you're driving down a highway, right? You're going like 60 miles an hour.
Okay, pretty fast.
Yeah. Now, close your eyes, make 3 sudden, completely distinct steering adjustments based entirely on what the road looked like a second ago, and then open your eyes again, just hoping you didn't crash.
That sounds like a terrible idea.
It's a horrible idea. But in the world of robotic learning, this is basically what we call action chunking. And surprisingly enough, it is the secret engine powering today's most advanced robots.
Yeah, it really is.
Welcome to AI Paper Slop. Today we are diving into a paper that's just fundamentally challenging how we build robotic foundation models. It's called Why Does Action Chunking Improve Behavioral Cloning Performance in Robotic Control? By Filippo Azzati and a joint team from UC Berkeley and Politecnico di Milano.
Right, and if you are building robot learning systems right now or, working with vision language action models, you really need to hear this. Because action chunking, which is basically that practice of predicting a whole sequence of future actions from just one current observation, it's the absolute backbone of state-of-the-art behavioral cloning.
We're talking about models like Aloha Diffusion Policy, Pi Zero.
Exactly. But the field's standard explanations for why this chunking actually works, like the assumptions around temporal consistency, horizon reduction, representation learning, they're incomplete. And the authors argue they're often just mathematically wrong.
Wait, really? Mathematically wrong?
Yeah. This paper proves that action chunking actually works due to 3 hidden mechanisms. You have non-Markovian expressivity, reduced compounding error by predicting from past observations, and crucially, it's acting as an implicit ensemble of temporal relationships.
That is wild.
And the real kicker is their proof that we can beat standard action chunking entirely just by building explicit ensembles of delayed policies.
Okay, let's unpack this. Because to really grasp the significance of debunking these foundational theories, we kind of need to establish the baseline, right? Like how behavioral cloning usually operates for the researchers out there.
Yeah, that's a good place to start.
So in a standard purely Markovian setup, the robot observes its current state. Let's call it the observation at time t, or O sub t.
Right.
And based solely on that single image or state vector, the model predicts the single next action, a sub t. The robot executes that one action, takes a new observation at t plus 1, and just repeats the cycle.
Exactly. That is the classic reactive loop. Every single decision is based exclusively on the present moment, but action chunking, it just completely shatters that paradigm.
Oh, because you're doing a whole sequence.
Yeah, instead of predicting one action, you observe O sub t, and you force the model to predict an entire sequence of future actions. So a sub t plus 1, all the way up to, say, a sub t plus k minus 1.
So a chunk of k steps.
Right. And then the robot executes some or all of this sequence in an open loop fashion. Like it physically moves through those steps before it even bothers to process a new observation from the environment.
And pretty much all modern robotic foundation models rely on this, right?
Literally all of them. It's everywhere.
Which brings me back to my highway driving analogy, because that sounds completely counterintuitive for a physical system.
It really does.
Like open loop execution means you are intentionally ignoring the environment for k steps.
Yeah.
If the environment changes, or I don't know, if the robot slips on something, it has no idea until the chunk is finished.
It's flying blind.
Exactly. So why on earth would ignoring the physical world actually improve a robot's success rate in reactive control tasks?
Well, that paradox is the exact mystery this paper investigates. For years, the first hypothesis the field leaned on to explain this counterintuitive success was temporal consistency.
Okay, temporal consistency.
Yeah.
How did that logic go?
The logic was basically that human demonstrators don't just react frame by frame like a flickering robot. Human motion is smooth, right? It's correlated and continuous over time.
Right. We don't move in jittery stops and starts.
Exactly. So the widespread assumption was that by forcing a neural network to predict a whole chunk of actions at once, you force the output to be a smooth, temporally consistent sequence.
Ah, I see.
Yeah, and that theoretically prevents the jittery, contradictory, and honestly catastrophic actions you sometimes get from standard frame-by-frame Markovian policies.
I see the logic. You want the robot to move like a human, so you force it to plan a continuous human-like trajectory.
Makes sense on paper.
Right. So the researchers put this assumption to the test on the Libero 90 benchmark. And they found a really surprising nuance in how humans actually move, didn't they?
They did. They confirmed that human demonstrators are indeed non-Markovian, but not just because they are quote-unquote smooth. The paper highlights this perfect mechanical example. It's Libero 90 Task 6.
Which one is that?
It's a task that involves a robot arm opening a bottom drawer. When a human teleoperates the robot to reach the drawer handle, they don't just fluidly grab it and instantly yank it back in one unbroken motion.
Right, that would be unnatural.
Exactly. They reach the handle and they actually pause.
They hit a decision boundary.
Yes. They pause to ensure a solid physical grasp before changing their kinetic direction. Now, think about what happens if you train a purely Markovian single-frame policy on that specific human data.
It probably panics at that decision boundary.
Yeah, complete panic. It looks at the current observation, which is just a static image of the robotic hand resting on the drawer handle. But in the training data set, sometimes that specific visual state corresponds to the human paused and waiting.
Oh, I see.
And other times, that exact same visual state corresponds to the human pulling the drawer backward.
Because it only has the current frame. It has no memory of how long it's been resting on the handle.
Exactly. It lacks the temporal context entirely. So standard behavioral cloning does what it always does with conflicting data.
It averages it.
It averages it. The network averages weight and pull together into this catastrophic trembling failure where the robot basically just vibrates in place. It's trying to remain still and move backwards simultaneously.
Wow. And action chunking solves this trembling, right?
Yeah.
Because predicting a sequence gives it the context of the whole motion.
Right.
But here is the massive twist the authors uncover. They prove that you don't actually need to predict a temporally consistent sequence to solve the pause.
No, you don't.
They introduced this concept called a delayed policy. So instead of predicting a sequence of future actions, you just predict the current single action, a sub t, but you condition it on an observation from n steps ago.
So you predict a sub t given O sub t minus n.
Exactly. And they show that this single-step delayed policy perfectly captures the non-Markovian pausing behavior. It totally matches the success rate of complex action chunking.
What's fascinating here is that temporal consistency across a predicted sequence isn't the active ingredient at all. The strict requirement isn't to predict a smooth future. The requirement is simply to condition your current decision on the past. By looking at an observation from, say, 10 steps ago, the policy effectively gains the internal temporal context needed to deduce, okay, I've been at this handle for 10 frames now, the pause is over, it's time to pull.
Wait, hold on though. If I'm trying to yank open a sticky drawer right now, why is looking at an image from 10 frames ago fundamentally better than looking at the image right in front of me?
It sounds weird, doesn't it?
It feels like trying to catch a fast-moving baseball by staring at where the pitcher was standing 3 seconds ago.
Well,
You're intentionally using outdated information to make a real-time physical decision.
And that skepticism leads directly into the second major hypothesis the paper dismantles, which is horizon reduction.
Okay, let's get into that.
So for a long time, the community assumed action chunking worked because it effectively shortened the length of the task. Like, if a task takes 100 steps and you execute chunks of 10 steps at a time.
The neural network is only making 10 discrete decisions instead of 100.
Precisely. And the assumption was that making fewer decisions reduces compounding errors.
Let's translate that math for the listener, because compounding error in supervised learning is notorious. If you make a tiny mistake on step 1, step 2 is now operating in a slightly unfamiliar state.
Yeah, the paper formalizes this in Theorem 1. They prove mathematically that in a standard Markovian setup, your errors don't just add up, they multiply.
Oh boy.
The suboptimality scales exponentially based on the horizon. If your horizon, meaning the total number of steps, is h, your error explodes at a rate proportional to 2 to the power of h.
2 to the power of h. That is a brutal reality of behavioral cloning.
It really is. Every tiny physical drift puts you further out of the training distribution, making the next prediction even worse.
So the old theory was chunking makes h smaller, so the exponent is smaller. But Theorem 2 drops the hammer on that idea, doesn't it?
It completely drops the hammer. Theorem 2 proves that you don't need to reduce the horizon to fix the exponential explosion.
Wait, so how do you fix it?
Predicting actions from past observations, that delayed policy we just talked about, mitigates compounding error just as effectively as reducing the horizon.
Really? Just looking at the past fixes the compounding error.
Yeah. And the math behind why is beautifully elegant. Imagine you are predicting your current action, a sub t, based on your current observation, O sub. But your physical robot has been drifting slightly off the optimal path for the last 50 steps.
Okay, so it's a bit off track.
More than a bit. Your current observation O sub t is highly out of distribution. It doesn't look like anything in your clean training data.
You are officially lost in the woods.
Exactly. But if you predict your current action A sub t based on an observation from 10 steps ago, O sub t minus 10, well, that earlier state has compounded 10 fewer steps of physical error.
Oh, wow. I see.
It is significantly closer to the true, safe demonstration distribution. You are basically anchoring your current real-time action to a past state that is far more reliable and in distribution than your current messed-up state.
That is brilliant. It's like taking a highly complex math test. If you base your next calculation purely on your previous line of work, and you made a tiny arithmetic mistake early on, that error just spirals, and your final answer is wildly wrong.
Right.
But if you base your next calculation by constantly referencing the original prompt from 5 minutes ago, you stay on track. You anchor yourself to the ground truth rather than your own compounding mistakes.
That captures the mechanism perfectly. And, just to close the loop on the old theories, the authors also evaluate hypothesis 3, which is representation learning.
Oh, right. The idea that chunking acts as a good auxiliary loss.
Yeah, some researchers argued that forcing a network to predict a long sequence builds better internal representations. The authors tested this comprehensively.
Yeah.
They found that while chunking does provide a representation learning signal for very short horizons, simple delayed policies achieve the exact same representational benefits for longer horizons.
It's not the chunking.
Nope. Action chunking itself, the actual act of outputting a sequence, isn't the magic ingredient at all.
Okay, I'm tracking with all of this. Single-step delayed policies can match action chunking on temporal consistency, they sidestep the compounding error, and they get the same representation learning.
Yeah.
But here is where I'm stuck. If that is all true, why do empirical tests across the literature still sometimes show action chunking performing slightly better than a basic delayed policy? Like, what is the missing variable that gives chunking its edge?
This is where the authors uncovered the true, hidden magic of action chunking. It comes down to a mechanism they call implicit ensembling.
Implicit ensembling. Okay, break that down for us.
To understand this, we really have to look closely at what is physically happening inside the neural network's weights during the training loop. Think about training a policy to predict an action chunk of size k. From the observation at time t, you predict actions for t, t plus 1, all the way to t plus k minus 1.
Right, that's one forward pass.
Yeah, step forward one single time step in the training data. You take the observation at t plus 1, and you predict a brand new chunk. That new chunk predicts an action for t plus 1, but this time it's the first action in the sequence, based on O sub t plus 1. Notice what just happened to the action at time t plus 1.
Wait, it got predicted twice? Once by the previous chunk and once by the current chunk.
Exactly. And during backpropagation, the neural network's loss function evaluates all of those predictions. This means the network's hidden layers are receiving gradient updates to accurately predict the action at t plus 1 based on the current observation, based on the observation 1 step ago, 2 steps ago, all the way up to t steps ago.
Oh, wow. So the network is simultaneously forced to learn all these different temporal relationships at the exact same time?
Yes.
Wait, let me make sure I understand this, though. How can it be an ensemble if there's only one model? When I think of ensembling and machine learning, I think of training, like 5 entirely different ResNet models and having them vote on an output. Where are the other models coming from here?
Well, they don't exist as separate models. They exist as overlapping temporal perspectives forced into a single set of weights. An action-chunked policy predicting a sequence of k actions is mathematically acting as an implicit ensemble of k different delayed policies.
That is wild.
Because the weights have to minimize the loss across all those different time delays simultaneously during training, the internal representation becomes incredibly robust. And, decades of machine learning tell us that ensembling, averaging the predictions of multiple perspectives, massively increases robustness and reduces variance.
It's like asking a single chess grandmaster for advice on your next move. But instead of just showing them the board right now, you force them to look at the board as it is right now, as it looked 1 move ago and as it looked 2 moves ago.
I love that analogy.
Even though it's just one brain, forcing that single network to synthesize and satisfy those 3 different temporal perspectives gives you a vastly more robust move than just showing them the current board.
If we connect this to the bigger picture of robotic foundation models, this entirely explains why vision language action models scale so incredibly well with action chunking.
Right.
The field assumed we were just handing the robot a smooth trajectory to blindly follow. In reality, we were accidentally leveraging the immense statistical variance reduction of temporal ensembles without ever explicitly training multiple separate models.
We were getting ensemble generalization completely for free.
Completely for free, under the hood.
Here's where it gets really interesting for the engineers listening. If the only reason action chunking is working is because it is secretly just a disguised ensemble of delayed observations, we should be able to rip the chunking card out entirely.
Yep.
Like, we should be able to explicitly build an ensemble of delays and get the exact same or maybe even better results without ever predicting a sequence, right?
And that's exactly what they did. The researchers followed that exact thread for their practical experiments. They set out to beat action chunking at its own game.
How did they do it?
First, they created the randomized-delay ensemble, or RDE. Instead of outputting a sequence of actions and executing them open loop, the RDE is just a single-step policy. But at every single time step, it randomly selects a delayed, pulls the observation from D steps ago, and predicts the current action.
So it's rapidly swapping between different temporal perspectives, frame by frame.
Yes. And not only did it rapidly swap, but this RDE perfectly matched the success rate of standard complex action chunking.
That alone is huge.
But they took it a step further. What happens if you don't just randomly swap, but you explicitly ensemble them at inference time?
Okay, so you query the policy for the action based on the current frame, the frame 1 step ago, 2 steps ago.
And you mathematically average those predictions together before the robot physically moves.
The ultimate wisdom of the crowds. But the crowd is entirely made up of the robot's own short-term memory.
Exactly. And by explicitly ensembling these delayed policies, they outperform standard action chunking across the board.
Across the board.
They validated this on the simulated Libero benchmark. They validated it on the Robomimic datasets. And most importantly, they proved it in the real physical world.
Well, simulation is great for proving math, but a physics engine is perfectly clean. It isn't a slippery, unpredictable real-world kitchen. Did these explicit delayed ensembles actually work when they put them on a physical robot trying to manipulate real objects?
They absolutely did. They deployed these explicit delayed ensembles on real bimanual robots, performing some pretty complex tasks, like picking up a slippery carrot and putting it in a bowl, placing a soft slice of bread into a toaster, and dropping a delicate piece of sushi into a cup.
Oh man, a slippery carrot. Think about the physics of that. If you are using standard open-loop chunking and the carrot slips in the robot's gripper at step 2 of a 10-step chunk,
the robot is blind to that slip for the next 8 steps.
it will just crush the carrot or drop it entirely.
Yeah.
Because it's committed to the sequence.
Exactly. But the explicit delayed ensemble is reacted at every single step while still being stabilized by past context. In every single real-world task, the explicit delay ensembles successfully matched or exceeded standard action chunking.
That is incredible.
And it achieved this without predicting a single sequence of future actions. The robot was purely reactive, single-step, but intelligently querying its own past.
So, putting on my pragmatic ML engineer hat for a second, if I'm training a state-of-the-art diffusion policy for a hardware startup today, should I just rip action chunking out of my code base immediately and replace it with these explicit delay ensembles?
Well, you have to weigh the hardware and engineering realities. Action chunking remains incredibly efficient for inference speed.
Ah, right.
Because if you predict 10 actions at once and execute them open loop, you only have to run a massive computationally heavy forward pass through your diffusion model once every 10 steps.
That makes sense. That is a massive computational saving, which is vital when you are running a 7 million parameter VLA model on a physical robot with tight latency and compute constraints.
Right. Querying an explicit ensemble of 10 different delays at every single physical frame sounds computationally punishing for real-time control.
Yeah, that would fry the onboard compute.
It is computationally expensive. However, understanding this underlying mechanism allows researchers to push the state-of-the-art much further.
How so?
Well, if you know that the performance edge actually comes from ensembling delays, you aren't locked into arbitrary fixed chunk sizes anymore. You could train a model to dynamically select the optimal delay based on the variance of the predictions.
Oh, that's smart.
Or, more practically, you could distill a heavy explicit ensemble of delayed policies into a much faster single-step model for deployment. This paper shifts the entire paradigm from asking, how long should my action chunk be, to asking, what temporal perspectives does my model need to see to reduce variance?
That is a massive conceptual shift. It completely reframes how we think about the flow of time and memory in robot learning.
It really does.
And it actually brings me to a final thought for you, the listener, to kind of mull over. If implicit ensembling of delayed observations is the secret sauce for reducing compounding error in robotics, it makes you wonder about the architecture of autoregressive language models.
Well, that's an interesting connection.
Right? Because LLMs suffer from massive compounding error and long reasoning chains. If they make a slight logical mistake early in a complex proof, that error spirals out of control because the context window is now corrupted.
Yep, the exact same exponential explosion.
So what if, instead of just predicting the next token based strictly on the immediate context window, we use randomized delay ensembles to average predictions based on different past token states? Could we get the robust reasoning benefits of chain of thought just by explicitly ensembling delayed temporal predictions?
The parallels between spatial compounding error and linguistic compounding error are just striking. It's definitely a theoretical space to watch.
It's a wild thought. But if roboticists are finding their breakthrough answers by looking into the past, maybe natural language processing should be looking there too. That is all the time we have for this deep dive on AI paper slop. Keep digging into the research, keep questioning the defaults, and we will catch you next time.